Hey guys, Romel, Leo, Tyler, Sue, good morning. Today we're going to talk about fluorescence, and I'll give you the data to do a simple uh, lab. And we're going to look at the fluorescence of a fluorescent dye called rhodamine 6G. And there's actually three spectra that we're going to process. Two of them are described in the lab here, and there's a third we'll add alongside it. And the three spectra are absorbance, then fluorescence excitation, and fluorescence emission. And hopefully what we'll see is that the absorption spectrum looks a lot like the excitation spectrum. That is, the absorption spectrum looks like a lot like the fluorescence excitation spectrum. And the emission spectrum looks a little bit like, hey Kenya, and the emission spectrum looks a little bit like a mirror image of the excitation, or a mirror image of the absorption spectrum. So I would like to start this conversation off with a conversation about the electronic levels available in rhodamine and a lot of similar dye molecules. And basically, there's three distinct levels that we see spectroscopically. There's the ground state. Oops, that's not good. Okay. There's it's messing with me. Let's see here. I want to see where this writing is ending up, if it's ending up on a different page or something like that. Just disappearing, huh? I want to record it in the lab notebook because I want to put it, I want to clean it up and put it here permanently. Let's see here. Okay, well, I guess I'll have to get a whiteboard. Hold on. let's see here, I'm going to change the share. Let's see here, new share. This is whiteboard, maybe? No, this whiteboard. All right, you guys, can you see me writing, making squiggles?
Yep.
Yeah.
Excellent, thank you. Okay, so for rhodamine, R6G, there are three important levels. There's a ground state, an excited state, and a triplet state. So there's this S0, S1, oops, and T1, right? And each of these states has, a number of vibrational substates here, which we will not resolve, but we'll be able to see the width of the peak, because there will be some mixing of these vibrational modes, right? So actually, I'm not sure that this is a triplet state. This is it could be another singlet state, because the lifetime is very short. So and also it's accessible by absorption, so that indicates that it's probably another singlet state. But basically, you can imagine going through the ultraviolet spectrum in let's change colors here, and let's do an ultraviolet spectrum in theory here. So we start with long wavelength light, right? What's going to happen here is that we'll start with an excitation arrow that maybe is, say, this long, right? This may correspond to, say, 800 nanometers or something like that. And then as we scan down to, say, 200 nanometers, then we're going to wind up with an energy, a higher energy here, which is greater than most of the S1 levels that we're going to look at, right? So and as we go through, and we're going to lengthen this arrow, right? And we're as we go through here, we're going to start out with 800 nanometers here, and then we're going to keep going. We're going to go and go and go and go, and then we're going to start to observe a peak, right? And then we're going to go, we're going to go, we're going to go, we're going to go. Then the peak will disappear, right? And then we'll go, 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 and then a new peaks. Are observed, and then we run out of gas. Right, and so this blue here is going to be the absorbance spectrum, and if we plot absorbance versus wavelength here, we can do a sort of a Gedanken experiment where we go from, say, 800 to 200 nanometers. We're starting out here, this is 800, and then this is maybe, let's see here, this is probably about 600, maybe 500, and then 2, and then 300 and 200. And so we're going to start here, and we won't see anything, right? Until we get to this first peak, right? And this is the, let's forget the T1, let's call this S2, right? This will be S0 to S2. And then it goes back down to 0 again. And then when we get up to, say, around 300 nanometers, this guy might be around 500 nanometers. And we'll see more peaks, right? And this is just, I'm only doing this to make the one point, which is that as you scan along a spectral axis here, you scan through the available energy states of the molecule, right? And fluorescent molecules, they have, like rhodamine, it has a lot of aromatic character. It has fused aromatic rings. It has a lot of conjugation. And so there is a large visible feature, right? And this is due to the aromatic, let's say, not necessarily aromatic, but the highly conjugated nature of R6G. So now another thing that happens with rhodamine is that rhodamine can also emit light, but it emits light mainly from this level right here. So it emits from this S2 state here. And I guess I should probably write this in red because I'm going to talk about a different phenomenon here, right? And so, for example, if we put 200 nanometer light in, actually, I'm gonna have to erase a whole bunch of stuff here, but fortunately, this is all being recorded on video, and we can take a look at it later. So I'll erase all the absorption stuff, and let's write in some excitation. Right? And let's say that we're going to do some excitation spectra, and we're going to start and we're going to start at 200 nanometers. Probably 220 would be more realistic. And then we'll scan this guy out to say maybe 490. There's a good reason to stop there. So what's going to happen is we're going to start our excitation spectrum with light having an energy way up here. And then we're gonna slowly make that light less and less energetic, right? Actually, I think we can probably go to 590 actually. And then what we're gonna do is we're gonna get all the way pretty much to the bottom of this well here. Okay. And all these arrows come down all the way to the base here. I just haven't drawn them in quite perfectly, right? And in an excitation spectrum, what we're going to do is we're going to take ultraviolet and some visible light here. Oops, I got a highlighter here. Is we're going to take some light from what's called an excitation monochromator. And then that light, we can set the wavelength, right? And we'll direct that into a cuvette containing the rhodamine 6G. Right? And then what we're going to do is we're going to look at the light that emits. And so we're going to, literally we're going to excite and look at emission at right angles. So this is going to go into the emission monochromator as a function of wavelength, right? Now, for excitation, we're going to scan the excitation wavelength, just as I've described here. So we're going to scan the wavelength such that the molecule starts at this ground state and is excited into these upper states. Then what we're going to do is we're going to look at the emission that comes out right around here. Okay. So this is scanned and this is fixed. And we're starting with the high energies and we're going to go to the low energies. And pretty much what we see is a copy that looks like that. So the red here is now the excitation spectrum. So I said, well, why do they look the same? Well, what happens is that I'm going to make a little space for myself here, eliminate some of these lines. As let's say we can start at the very beginning wavelength, right? And what we see happening is that as we excite the molecule into this state up here, there's some state up here that it excites into. And then what happens is that the molecule decays down very quickly into this state. And that state decays into this state. And that state decays down there. Well, that's this state then decays down here, and then that emits light. Let me see. I need a new color here for emission. I'll make it blue here. And then there's a blue emission. It's actually a red emission, which is unfortunate choice of colors on my behalf. But so this is the excitation, and this is the emission. Hold on just one sec, folks. I gotta field the text. All right. So now the question is, what happens when we scan the excitation wavelength? What happens when we change this wavelength? Well, let's just go through that here. And first, we're exciting into this state up here, right? And we're going to make this progressively longer, right? And progressively longer. And as we're going through these states, we're able to couple energy into the molecule through these states, which then decays and emits at this wavelength out here. Right? So let's see here. We can call this lambda EM, right, for the emission wavelength. And and what happens, the sort of the energy flow here is that we go energy in, and then energy comes out like that, right? And then so long as we're going into real states here. So let me make these guys red here. Let's see. As long as we're going into real states, then there's a mechanism for the molecule to translate these energies up here into this emission energy out here, so into this emission wavelength. So we got energy going in, high energy going in, and low energy coming out of the molecule. So EX is energy in, and EM is energy out. You know, and this is referred to also as fluorescence or luminescence or possibly even phosphorescence. But in this particular case, it's fluorescence, right? Fluorescence or luminescence. Phosphorescence definitely involves a triplet state, and it's a longer lived triplet state. So this is an excitation spectrum, right? This red one. So the red guy here is an excitation spectrum. And now it's possible to collect an excitation spectrum on an extremely dilute solution, a solution that's way too dilute to actually collect absorption data. And that's one of the interesting things about fluorescence, right? Is that because the sample is the source, there's really no worries about there's no real worries about ratioing to a reference beam. So you don't need to have a single detector that can span many orders of magnitude of sensitivity, right? And so basically, the sensitivity of fluorescence depends on how efficient the molecule is in emitting light, you know. So, for example, with rhodamine molecules, you can literally detect a single molecule. You know, that's 10 to the minus 23 moles. You know, that's just ridiculous. You know, ridiculously low concentration. Um, uh, so, and you know, and that there's a variety of ways to do this. Like you can do it under a microscope. You can illuminate a small patch using the ATR method. If you've got a molecule sitting on a surface, you can see the molecule light up against the black background, or you can suspend it in a droplet, you know, and focus a laser on the droplet, and then look at the longer wavelength. Look at the red shifted light, and you can literally see the emission of a single molecule. And that in itself is just a fascinating area of study because sometimes you can see the molecule changing, like if you have the molecule embedded in a plastic, for example, and the plastic is near its glass transition state, it's warm enough that it's just slightly liquidy, then you can see the fluorophore tumbling. You can see it changing states very, very slowly and going through various conformational state changes. So, but in any case, what we're going to focus on today is the absorption, excitation, and emission spectrum of rhodamine 6G. So now we just talked about the excitation spectrum, and I've been talking for literally 30 minutes nonstop here. And so I need to engage one or more of you a little bit in some conversation about this and see how we're doing in terms of understanding stuff. So even though this is almost never ever sort of works, I'm sorry, but let me just open it up for questions and see if there are any kind of questions that have. Okay. So so when we do excitation spectra, do we monitor the emitted wavelength, the emitted radiation at a longer or a shorter wavelength than the excitation? I'll write that in the chat box here. Okay, good. So William says longer. Who else can weigh in on that? It says longer, longer question mark. So monitor, by monitor, I mean, do we measure the light coming out? We put light in, and then do we measure light coming out at a longer or a shorter? Leo, what's your answer here? I know you know.
I think it should be longer because the energy coming out is going to be less than the energy coming in. So the wavelength should be longer.
Exactly right. Exactly right. Exactly right. Kenya, do you agree? Dr. Escobar? Uh-oh. What is that? Oh. Are those eyes or is that uh-oh?
Oh.
Oh, I see. I would say O-O-H. Oh, of realization. Got it. All right. So so basically Leo and Tyler are completely correct here. That the when you look at the the output of the molecule, it really has no mechanism to absorb more than the photon energy. Right? These are fairly large energies. For example, the excitation is about 4 electron volts, maybe 5. So the potential energy change of the electron going from the ground electronic state configuration to the upper electronic state, S1, S0 to S1 there is about 5 volts. And that's in the ultraviolet part of the spectrum, maybe 100,000 degrees centigrade or something. Excuse me, sorry. Okay. So now let me ask another question here. Then we can possibly move on. So why does the absorption and the emission, why do they look similar? That may be too stupid of a question. Okay, so let's see here. Okay, I'll use black here. For the emission spectrum here, we excite and we collect radiation at right angles. The light that we collect here, are these the exact same photons that went in to do the excitation? Or are these newly created photons? Oops.
I think they are the same photons, but they just have lower intensity.
Ah, that's really interesting. Uh-huh. Okay, So, um, uh, so Leo is saying that they're the same photons but lower intensity. And this brings about a really important distinction in spectroscopy that um, uh, these these are actually and Kenya says they're the same, and
Wait, are you talking about the light or are you talking about the molecules? Because in spec you're looking at the movement, like the vibration, right, and stuff of the molecule
uh-huh,
with the photon. Is that
uh-huh,
correct?
exactly right, exactly right. So the photon comes in, interacts with the molecule, right? And there's two ways to look at this, right? Either you can monitor the amount of light that's lost, right? So the light comes in here, and then some of that light is lost as a function of wavelength coming out. So this is what we call absorption, right? But then for emission, this for or fluorescence excitation spectroscopy, actually, we're looking at a new photon at a new wavelength, right? And that new, I refer to these as new photons, right? Because a photon is absorbed by the molecule, and that photon is then gone. It's lost. Its energy is taken up by the molecule, which then gives some away as heat, and then emits, and then changes state, gives more away as heat, right? And then emits, right? So these are new photons, actually. Does that make sense? Romel, how are you following?
I'm like in the middle, so.
Okay, alrighty. Um, so in absorbance spectroscopy, right? You've got a light source here. You've got your source. Oops. And it's basically just a fancy light bulb. And then it goes through a monochromator. And then one wavelength comes out, right? And that one wavelength interacts with the sample. And then relative to a blank, you can calculate how much of that light is absorbed, right? Absorbed by the molecules. Does that make sense? Kenya says yes, Romel says yes. Good, excellent. So, and basically by changing the wavelength, by changing the energy, you can scan through these states, right? You can scan through all these different states here. Does that make sense? William says, oh, good, excellent. Tyler, how you doing? Good? Sue? You tracking, Sue? Good, good, okay, cool. So you should be able to answer then the question about inabsorbance. Let me ask this. In absorbance spectra, are the photons detected the same photons that come from the source? let's see how Sue, how do you do with this one? It's kind of a strange question, but see how you can do answering it. They're not the same. Okay, so explain to me what you mean by that. Or is it just not really clear? Okay, so yeah, they're the same, but I want Sue to like weigh in on okay. So your original answer was that they were different photons, right, Sue? And so, and what I'm saying is that the photon is, if the photon goes through, it's detected. If it doesn't go through, then it's not detected, and that's a signal, right? The signal is that the photon was not detected. Does that make sense? Okay, good, excellent. So now in emission spectron or in excitation spectroscopy, right? You're going to vary the frequency of light coming in or the wavelength of light coming in, but then you're just going to look at light coming out at this one specific wavelength that corresponds to basically this transition here, right? That one longer wavelength transition, this guy right here. Okay, now I'm going to ask you again, Sue, to say, are these emitted photons, are these the same photons? The same photons that were from the source. Sue, was that a yes? Okay, so that is not true, because what happens is that there's a photon plus a molecule that makes an excited state. The excited state goes to a new excited state, and then the new excited state goes back to the ground state, plus a new photon. Right? Does that make sense? Somebody say yes. Yes. Tyler? Use. Good. Excellent, good. So now, excitation spectroscopy is when you change the frequency of the source, right? When you change this source wavelength, right? And so that means you're scanning the excitation along this axis, right? And you're just looking at this one wavelength where stuff comes out. Now, emission spectroscopy means that you put light in. Okay, actually, I need a new color to talk about emission. Geesh. Emission spectroscopy is where you put light in at a short wavelength, and then you monitor the wavelength at which it's emitted, right? And it's really interesting because you can put the emission spectrum is not going to have any features at all in the ultraviolet. And it's not even going to have anything here until we get up to about this range. And then it's going to look like the mirror image. It basically has a steep side and a sloping side. There's a sloping and a steep and a steep and a sloping side. And basically what you're seeing is that as you, for the emission spectrum, as you put in light in here, right, then you monitor where the light comes out. You monitor on the red side of that line, you know, you say, is it here? Is it here? Is it here? Is it here? You know? And then you don't start seeing it until you get down to here, right? That's where you actually start seeing the stupid emission. And it sort of maps out the vibrational manifold of the ground state that way. And so in emission, you fix the excitation and you scan the emission spectrometer. Does that make sense? So Leo, let me ask you a question about this. Is the emission wavelength longer or shorter than the excitation?
It's longer.
Yes. Yes, it's longer. Right. So when you do emission spectroscopy, and you excite at, say, 300 nanometers, at what wavelength can you begin scanning the emission?
Would it still be the same as the 200 or, oh no, it goes backwards, so 800?
So if you okay, so right, if you excite at 300, right, that means, let's say this is exactly 300 nanometers here, just for giggles, right? And if you look at the emission at exactly the same wavelength, what you're going to see is two things. You can see resonance fluorescence, right? That is, if it gives you back exactly the same wavelength that you gave it, that's called resonance fluorescence. But then also what you can see is Rayleigh scattering, which is another form of, it's kind of hard to say whether they are the exact same photons. It's sort of more accepted, oh, they're the same photons or something. Because the processors are instantaneous, you know, the scattering phenomena. But you can see resonance fluorescence, but typically what you're not really interested in either of those processes, right? What we're interested in seeing are the processes that happen at slightly longer wavelengths, right? So given the performance of the monochromator, typically you would start at about 310 nanometers to scan the emission. Does that make sense? And you're looking at, okay, here's a good question for Tyler. Are these Stokes or anti-Stokes shifts? Or you could also answer, are these red or blue shifts? They are definitely red shifts, right? And red is Stokes. Okie dokie. So let's accept for the moment that there are three types of spectroscopy that we can do. There is absorption, where photon loss is the signal. And literally, there's source, monochromator, sample, and then detector. And there's a direct line between the source and the sample, the source and the detector, right? This is in a line or a straight line. In fluorescence excitation, you've got source, monochromator for the excitation, then you've got sample, then you've got monochromator for the emission, and then detector. So these come at right angles. Does that make sense? And so let me ask a question here. In excitation, is the excitation, monochromator, or the emission monochromator scanned? Do you know the answer, Romeo? Okay, Kenya, why don't you answer?
Because in order to detect it, like, doesn't it have to go through the detector itself? And isn't that a way of scanning it, I suppose?
Uh, so, um, uh, so the light uh, has to be sorted by wavelength before it's detected, right?
Mm-hmm.
And in absorbance, right? It's the sorting happens here, right? Then the same light that is absorbed is detected, right? So the same light that comes from the source. Oh my God, what happened there? Sorry. The same light that comes from the source is detected, and then a loss of that light is the signal, right? In the excitation experiment, the source here creates light. The excitation monochromator sorts it. Then the emission monochromator sorts it again, right? Because this could be, 300, and this could be 550 nanometers, right? There are two different wavelengths, right? So you need two monochromators.
Okay.
Got it. Cool. So now, for the excitation experiment, as opposed to the emission one, is the excitation monochromator scanned or the emission monochromator scanned? Because in these experiments, excitation and emission, uh, uh, one is scanned, the other one is constant. So let me make a table here. Okay, so there's two answers here, right? And MC stands for monochromator, right? And Romel, what is the function of a monochromator? What is the function of a monochromator? So I can help a little bit. It takes, right, exactly. It takes broadband light and it produces narrowband light at a specific wavelength, right? So in these experiments I'm trying to describe here, the in excitation, one of these two monochromators scan. It's going to be the EX or the EM, right? So in excitation, which monochromator is scanned? EX or the EM? So we can look back here at the experiment that we're doing, right? For EX, the monochromator here, the excitation monochromator is scanned, and this arrow changes length, right? And you go through a range of wavelengths where you produce some peaks, and you go through a flat range in here, and you go through another set of overlapping peaks here, and then you stop, right? Because you can't scan over the emission line. Yes, exactly. Leo says EX for EX, EM for EM. That is correct. So this is EX, this is EM. Good. Does that make sense, Sue? So far, so good? Excellent, excellent. So I think what I'm going to do is I'm going to stop here. And you guys can, if you want to, you can look at the lab manual. But what I'm going to do on Wednesday, tomorrow, is at 8:30. I'm going to record another Zoom with the couple of students who show up for that lab. And then what I'll do is I'll go over the process of extracting the files from Canvas, and then graphing them, and then filling out the questions. It'll actually be probably only maybe a half an hour tomorrow to finish this up. But are there any questions that anybody has right now? Okay, kids. Well, then I will wrap up for today, and then I'll finish this tomorrow at 8:30 or 9. So probably at 9 o'clock tomorrow. So I'll put out a Zoom invite for 9 o'clock tomorrow. Alrighty, guys. Thank you so much.
Bye.
Bye, Kenya. Bye, Romel. Bye, William. Bye, Leo. Bye, Sue.